Greetings of the day, dear students. In this video, we are going to discuss about the voltage and current relation in delta connection, and also we will see its phasor diagram, and also we will do one example on this relation between the voltage and current in a delta connection. If we observe three three phase voltage source is connected in a delta manner. In this diagram, I1, I2 and I3 indicates the line currents. I1, I2 and I3 indicates the line currents, and IR, IY and IB, this IR, IY and IB indicates the phase currents. Now the voltage between the two lines, between the two line R and Y, in this connection, if you observe, the voltage between the two lines is same as the voltage across the phase R. So in delta connection, the phase voltage is same as the line voltage. Here VRY, VYB and VBR are these three are the line voltages and are also same as the phase voltages. Now one more important point, the phase currents will be 120 degrees apart from each other. That means the IR, as the system is balanced, all the three phases will have the same magnitude, but angle wise they will differ by 120 degrees. How do you understand that? The IR will be the magnitude wise same IP at an angle 0 degrees, and IY will be also having the same magnitude, some IP, let it be the magnitude is IP, but it should differ by an angle 120 degrees, so minus 120 degrees. And IB will also have the same magnitude IP, but it will differ by an angle 120 degrees with respect to the Y. So already minus 120 is there, and one more minus 120, minus 120 minus 120 minus 240 degrees we will get. Therefore, first we will plot IR at an angle 0. Later IY of same magnitude, but the angle difference between this IR and IY must be how much? 120 degrees, minus 120, right? You are rotating in the clockwise direction, minus 120. Now the angle between this IB and IY will be again 120, and IB and IR also will be 120. Oh, what I want to say is, in a three-phase balanced system, the voltage sources will have the same magnitude but will differ by 120 degrees with respect to the each other. Now this dotted line indicates the it's quite opposite, anti-phase. For example, IR minus IR is in anti-phase with IR. Similarly, minus IY and minus IB. With respect to the voltage, we got the clarity. The phase voltage is same as the line voltage with respect to the magnitude. Now, what could be the relation between this line current I1 and this phase current IR? That is what we are going to derive in this video. For that sake, observe, dear students, in the delta connection, at this node point, if you apply the KCL, this IR is entering current, IR is entering, but I1 is away from the node and IB also away from the node. Therefore, IR equal to I1 plus IB. IR equal to I1 plus IB. Therefore, I1 equal to IR minus IB. That is what we have done here. I1 is equal to how much? IR minus IB. This is IB. It's quite anti-phase, minus IB. This dotted line represents minus IB. Now let me add this IR and minus IB. So this is what? I1. I1 here indicates which current? Line current. IR is the phase current. Now if you observe, there is an angle difference of 30 degrees between line current and phase current. Line current and phase current. Because this angle between IR and IY, the angle is 120. But between IY and minus IY, it will be 180 degrees. Out of 180, this 120 is completed. Now this angle will be 60 degrees. This angle will be 60 degrees. Right? Now here let me apply the parallelogram law. We want its magnitude, I1 magnitude, I1 we want. I1 will be how much? Square root of, observe here from vector diagram, this by applying the parallelogram law, I1 will be how much? IR square plus IB square plus 2 IR IB, cosine of the angle between IR and IB, cos 60 degrees. Right? But IR, the magnitude of IR and IY and IB, let it be denoted with letter IP. They are the phase voltages. They will have the same magnitude. But angle wise there will be difference. Angle wise there will be 120 degrees apart from each other. Therefore, I1 equal to root over, in the place of IR and IB, we will substitute IP. Because magnitude will be same. Angle difference will be 120 degrees. Because the system is balanced. Right? Yeah. Now IP square plus 2 IP square into 1 by 2. We will get root 3 root over root of 3 IP square. It is simply root 3 times IP. Therefore, I1 indicates which current? In this context, I1 is our line current. Our line current is root 3 times phase current. Very, very important. In which connection? In delta connection. Whereas the magnitude voltage, line voltage is same as phase voltage. Whereas in star connection, if you have already watched the video, in star connection, line current is same as or will be same as phase current. But line voltage will be root 3 times the phase voltage. These four equations are very, very important. Just now we have seen for I1, the same we can apply for I2. I2 is the line current. At this node, if you apply the KCL, I2 equal to I1, IY minus IR. What will be the magnitude? Mod I2. Mod I2. Magnitude of I2 will be root over IY square plus IB square plus 2 IY IB cos of angle between those two, 60 degrees. Again, we will get root 3 IP. Therefore, if we observe, the line currents are root 3 times the phase current in delta connection. And another important observation you can make is, angle wise, line current lags the phase current by 30 degrees. One more observation, all the line currents are 120 degrees apart from each other. And the angle between, if this is the phase voltage and if this is the phase current, I phase, and the angle between the phase voltage and phase current will be is phi. Similarly, the angle between line current and phase voltages is 30 plus phi with the current lagging. So these are the four important observations. V phase equal to V line and I phase current equal to IL by root 3 in delta connection. Whereas in star connection, I phase equal to I line, phase current is same as line current. Whereas phase voltage equals to VL by root 3 magnitude wise in star connection. Clear? Right. Now, let me see an example. In this example, we are having a 400 voltage is applied to a delta connected balanced load having resistors 100 ohm in each phase. Find line current, phase current and power drawn. So First, let me draw the delta connected balanced load. And he has already given the line voltage between two lines is how much? 400 volts. And the connection is which connection? Delta connection. What about phase resistor values in each phase? Ra equal to Rb equal to Rc equal to 100 ohms. That is what we have drawn in this diagram. Now at this node point in this diagram, Ia indicates which current? Ia indicates the line current. Whereas the current from A to B, this I1 indicates which current? Flowing in this resistor Ra. This indicates the phase current I1 in this diagram. I1 is the phase current. I will write here I1, I2, I3 are phase currents. Similarly, Ia, Ib and Ic, these three currents are which currents? Line currents flowing in the line current. Clear? Now from the previous derivation, in delta connection, observe the line voltage is already given 400 volts. The same voltage is also across the phase. Both are in parallel. Therefore, the line voltage is equals to the phase voltage is equal to the magnitude wise how much? 400 volts. Now, once you know the voltage across A and B or A and C or B and C, the voltage is 400 volt. Resistor is 100 ohm. What will be the current? Therefore, current I phase equals to IL by root 3. But phase current is the voltage in the phase is 400 divided by resistor RA 100. So 4 amps. 4 amps is the which current? Phase current. 4 amps is the phase current. Now, once you know the I1, I2, I3 as the system is balanced, magnitude wise you will get the same values. Because for phase 2 also the voltage is same 400 only. Impedance is also given same 100. So you will get same 4 amps. Similarly for I3, V phase divided by RC, 400 divided by 100, 4 amps. Now what is the line current? Root 3 times phase current. Now what is phase current? 4 amps. Therefore the magnitude of the line current Ia will be how much? Root 3 into 4, 6.92 amps. 6.92 amps. In this problem, as the load is balanced, in the remaining phases also we will get the same magnitude of current. In case, for example, in the problem, if he has given different values of resistors, then you will get the different values of current. For example, if this is 100 ohm and this is some other 200 ohms and this is some 300 ohms, then we will get three different values of currents. But in this problem, all the resistors are same, right? Now we will get the same currents because the load is balanced. Now what will be the power? I repeat again, we have already discussed in the star connection, power equals to 3 VI cos phi root 3 VI cos phi. Both are correct only. But dear students, it's very important. Please keep in mind, if you have used 3, then the voltage and current values must be phase values. Very this is where the most of the students will commit the mistake. Simply sometimes they will write power P equal to 3 VI cos phi, but they will forget to take the phase values of voltage and current. Or sometimes they will substitute the line values. Then they will get the wrong answer. If you have used 3, right, then the voltage and current values must be phase values. If you have used root 3, then this voltage and current must be the line values. Please keep in mind. Root 3 VL IL cos phi or 3 times V phase I phase cos phi. Both the things are correct only. Now in this problem, what could be the value of cos phi? cosine of the angle between the voltage and current. The load is resistive, right? Now, in resistive case, voltage and current both will be in phase. There won't be any angle between the voltage and current. The angle is 0. Then what about cos 0 degrees? Sin 0, 0. Cos 0 is 1. Therefore, in this formula, cos phi is 1. Now already we know the values of root 3 VL, IL. VL is already given in the problem. In delta connection, line voltage is same as phase voltage. Therefore, root 3 into VL 400 into IL. Line current just now we have calculated. Line current is how much? 6.92. 6.92 into cos phi. Why it is 1? Because the load is resistive. The in phase, both the voltage and currents will be in phase. Right? Yeah. Now, dear students, in case, for example, if in the place of resistor, if he has given something, uh, if an impedance is given, for example, this phase is also, if you are given an impedance, if its value is 2 plus J3, right? Now, with respect to this phase, and here also 2 plus J3 is given in all the phases. In case if he has, instead of resistors, he has given the 2 plus J3. 2 plus J3. Now then the angle will not be 0 degrees. Theta equals to tan inverse of XL by R. The angle theta will be tan inverse of 3 by 2. That much will be the angle. Clear? Right. Now, in this case, we are given the resistors. Therefore, 4.794 kilowatt. 4.794 kilowatts. This is the power drawn by the circuit. If you observe, dear students, if you watch the previous video in star network, the same resistors connected in star manner, and we have applied the same voltage, same values of resistors. But in that problem, if you observe, the power drawn is only 1.59 kilowatt. So in delta connected, the power drawn is 3 times the power drawn in star. When all the resistors are same, keep in mind, when all the three resistors are of same value, then if once it is connected in star manner and again it is connected in delta manner, you can observe in delta network, the power drawn is 3 times compared to the star, right? Yeah. So in this entire discussion, dear students, the important point is in delta network, phase voltages, line voltages will be same magnitude wise, and the phase current will be IL by root 3. Clear? Right. Now, another observation is this angle, line current lags the phase current by 30 degrees. Line current lags the phase current by 30 degrees. How do you understand this statement? For example, if I write somewhere I phase equals to 5 at an angle 0, then what will be the line current? What will be the line current? Magnitude wise, you are familiar. Line current will be how much? Root 3 times phase current 5. But what will be the angle? This root 3 times from this formula, line current is root 3 times I phase. Magnitude wise, you are correct. But do you think here also the angle will be 0 degrees? Then your answer goes wrong. Magnitude wise, root 3 times I phase. But angle wise, this statement is important. Line current lags phase current by 30 degrees. If it is 0, here you will get minus 30 degrees. So if this is the phase current, if this is the phase current at an angle 0, Then if this is 90, 45, and this is somewhere 30. Magnitude wise more no, root 3 times no, you will get more current, more length line like this. But the angle difference will be how much? 30 degrees. This will be your line current. If it is a three-phase balanced voltage source, three-phase balanced voltage source, like that we have to understand. Clear? So, uh, just simply we will apply KCL at this node point and we will draw this diagram and we will specify the values of IR, IY, IB as phase currents and I1, I2, I3 are line currents depending upon the diagram. In some textbooks they may follow IA, IB, IC or some other notation. Some people may write it instead of the current flowing between R and Y, no, they may write it as IRY or IYR like that. They can represent the notation can be different. But depending upon the variables you have taken in the diagram, please follow that notation. The thing is, whatever current flows in this path is the phase current. In this path, in this line, line current. Variable names as you can choose on your own. Thank you.